Hello everyone, my name is Ingzi Jing, and with my group member Jacqueline Shenbin, we'd like to present you a final project, Perfect Maze Generation Algorithm. Our presentation will be broken into three parts: introduction, algorithm analysis, and conclusion. Introduction part. What is perfect maze, someone might ask? Well, so perfect maze is actually a specific category of maze with two unique characteristics. First, it has no loop in the past. Second, it has only one solution path. And the reason why we want to explore this topic is that for me personally, I have seen maze in our daily life a lot, whether it is in the pumpkin patch or in the video game. And then when I was playing the Legend of Zelda game, the exploration of like cave and dungeons provide me a great example of how developer integrate the video game design with the abstract algorithm knowledge. Therefore, I'd like to know more about the maze generation algorithm. In our final project, we have chosen specifically for algorithm, binary tree algorithm, depth first search algorithm, group scale algorithm, and primes algorithm. By analyzing the design and implementation of this algorithm, we will also assess its space and time complexity and its degree of randomness. And then at last, we will come to a conclusion of the optimality of certain algorithm. First, the binary tree algorithm. The binary tree algorithm is actually one of the simplest algorithms of the four. The fundamental idea of this algorithm is that starting from an initial cell, where at each step there are only two options available to create the path of perfect maze, moving up and down or moving left or right, depending on the choice. And iteratively, the entire process will move through every grid cell, gradually building the pathway in the designated direction. And in this process, we will eventually have a visible maze layout. So here I have an example pseudocode. So we have to iterate through all the cells in this grid and randomly choose a direction from up or down or left or right. And if that cell has a neighbor in this chosen direction from up and down, we can generate a path. Or else if the cell has a neighbor in the chosen direction from left or right, we also can generate a path in that direction. And last, we will return the modified grid. So the binary tree algorithm has three distinct characteristics. First is the lack of randomness. Actually, the lack of randomness is due to the fact that there are constantly only two options available when we want to extend the path of the maze. So as we can see in this generated result of 15 by 15 grid, there are strong diagonal bias here, which is from this way. So we can also see that these results are relatively identical, and there's like identical trend to the length of quadrant. And also, when we're talking about algorithms, the efficiency, which is often measured by time complexity, is crucial. And one benefit actually for the binary tree algorithm is that it has the linear time complexity. If we go back to the pseudocode here, we can see that we take n grid of time to go through on every grid, and in each grid we only take constant time to move. So consequently, if time efficient wise, we have a linear time complexity. Another crucial aspect that we look at is the memory usage, which can be measured by its space complexity. So here we can see that in the binary tree algorithm, it does not need to maintain any state. So the memory usage is actually relatively low. So the space complexity for the binary tree algorithm we can see here is constant, as it is based on the current cell during iteration and don't need to consider any other cell when proceeding. So by these three characteristics, we can see that the binary tree algorithm is best suitable for the case where randomness is not important, and for the case where small and medium-sized maze is being applied. So we can solve the maze in the linear time, and where the memory usage is stressed. Overall, I would say the efficiency of the binary tree algorithm is pretty high. Next, I will pass to Jacqueline.
Hello, everybody. I'm Jacqueline. I would like to introduce the depth-first search algorithm of maze generation and pathfinding. But firstly, I want to explain why I chose this topic. Most of people probably played maze since their younger age, like me. I found the interest of playing maze when I was very young, but as growing up, I found learning maze generation can solve real-world problems, such as network routing and optimizations. In addition, I feel like sometimes solving the maze problem is just like living in real life. You just need to try harder to find the way out. Then let's introduce a depth first algorithm to solve the maze problem. When considering the challenge of generating or solving a perfect maze, the DFS often comes as a primary method of choice. This algorithm is frequently used to solve problems that involve pathfinding. The basic idea of DFS to generate perfect maze is started from a random cell and explore unvisited cells, carving paths, and then backtracking when no unvisited neighbors were found. Now let's take a look at the implementation. The first part of the code would be to draw a grid of maze cells. I imported the Pygame of Python to draw the grid of maze cells and then set up constants such as colors of the wall and the cells, and mark all cells as blue means 8 unvisited cells, and mark the current cell as pink. And the second part of maze generation is mark the top left cell, the current cell, and mark it as visited. Where there are unvisited cells, choose randomly one of the unvisited neighbors to generate the maze until there are no unvisited cells. And the third part is finding the path. Begin at the starting cell, choose a direction to move, then continue in the direction as far as possible. If you reached a dead end, go back to the last point where you had more than one choice of direction. As exploring, marking the paths you've already traveled, so you don't repeat to visit them again. Keep exploring and backtracking until you find the end of the maze. And the time complexity is big O V, where V is the number of nodes and E is the number of edges in the maze. And the space complexity is big O V for the maze pathfinding, and it's the same. In conclusion, even though DFS is highly effective in maze generation and pathfinding, offering both recursive and iterative implementations, but it still doesn't guarantee a shortest path. So further research may need to improve its efficiency.
Hi everyone, this is Shengbin Jin. In my part, I want to introduce the Kruskal algorithm. As mentioned before, the project is to generate a perfect maze, which use different kind of the algorithm. In my part, I try to utilize the innovative application of this algorithm. Yeah, this is the SUI code for maze generation. I just defined the class and to set some important functions to this class. And then, yeah, speaking of the adaptation, in the maze context, the algorithm is adapted to add edges or remove walls randomly. Yeah, as for the disjoint set, yeah, if the wall is removed, the edge is added, the sets are united, illustrating the classic use of the union found structure in this algorithm. Yeah, this is the two very important library which I use in the this algorithm. The NumPy is utilized to represent the maze, and for the random library, it is to randomly select walls for potential removal. It's a very important part to achieve this algorithm. Yeah, speaking of the representation and the randomness, the maze will represent as a 2D grid using an array. Yeah, and then the visualization. This is the final visualization of my maze. It not only helps me in verifying the correctness of this algorithm, but also provide a very intuitive understanding of the maze structure. Yeah, and this is also the validation standard, yeah, which also helps me to whether the algorithm is working well. Yeah. Then we talk about the time complexity and the space complexity. Yeah, for my algorithm, the time complexity and the space complexity is the same. It's both the O W times H. W and H are the width and the height of the maze. Yeah, finally, I want to talk about the challenge and future perspective of this algorithm. Well, my algorithm will effective for some smaller mazes, but it's still hard to handle with the larger mazes. Therefore, addressing the scalability of this algorithm would be a very key area for future development. It's also a very potential avenue for the future research. Yeah, thank you.
Hi, I'm Zhen, and today I want to talk about the Prim's algorithm. First, I want to say I choose this topic because I got ideas from the AI Pigment project. It used maze as a test site, so I want to research it. And for this maze generation Prim's algorithm, it is different from the traditional Prim's algorithm that finds the MSTs. But the same point is they all use a greedy approach to find a locally optimal solution. This picture is the maze that the algorithm generated at start point, endpoint, and the solution path. The next step of the implementation. First, it initializes the maze by two-dimensional array that is filled with walls, and we start path generation from the start point S. So this picture is the maze looks like at the beginning. Next, it randomly selects the walls around the start point to try to remove as a new path. Make sure no path cycles are created after the removal because a perfect maze has no closed loops or isolate areas. The red, the red cell is a wall around the start point, and we do not choose the north and the west cell because outside is the border, and the border we cannot break it. Now is the core part. I use a list to store the wall around the current cell that may become path, or we can see the candidate path. Once it become a real path, sort it out of the list and add the walls around it in the list. The reason why not use stack as the data structure is stack follows the last in first out principle. But in the list, we can randomly choose next direction, which increase the randomness of the maze. So this is the current cell, and we can add them in the list. The last, repeat the last step until the list that stores the candidate path is empty. And now this algorithm ensures that all areas of the maze were interconnected without any isolate paths. So here I just choose the lower right corner as the endpoint E. And I didn't use any recursion in the maze generation function because in large maze, it might cause a stack flow error. Now let's talk about the complexity. If n represents the number of cells in the maze, in the worst case, the program might have to evaluate every cell except the border of the maze. So for time complexity, big O is On. In the best case, the algorithm's execution time is also proportional to the area of the maze. So big omega is N. And now we get big theta is theta N. In terms of memory usage, this algorithm requires storing the whole map, and there is no recursion inside. So we can see space complexity is big O. And overall, the Prim's algorithm is an excellent choice for generating perfect maze. It produces mazes without dead ends and usually have more path choices and a more complex maze structure, increasing the difficulty and fun of solving the maze. But if you want to create a larger and better maze, it may come at a higher space cost. After analyzing these four algorithms that we use, we can see in different situations and need, any of them could be the most optimal choice. But like I said before, Prim's algorithm might be an excellent choice overall. for generating perfect maze. It can generate complete maze in an acceptable amount of time, but sometimes it may come at a higher space cost. Here is a reference that we use in this PowerPoint. Thank you for listening.